So we've looked at how concentration affects the rate and how you can determine a rate law. Let's look at some of the other factors that can affect rate and how they affect rate. So temperature. So in general, increasing temperature can increase the rate of reaction. It can do it in two ways, okay? So two different ways. It can impact the number of collisions and it can impact the success of the collisions. So particles have more energy, they're moving around faster. So that's just gonna create more particles colliding. And then if more remember that you have to have a certain amount of energy to initiate a chemical reaction. So it can create more successful collisions. So more collisions, right? You have more kinetic energy, just means they're moving faster and they have higher velocity. Of the amount to increase the rate, it does only explain like a small fraction, as you kind of saw in kind of the virtual experiences that you've had. So in general, we usually say is an increase in temperature does increase the rate, but to kind of estimate it, usually a 10-degree temperature increase will double the rate. So, you know, going from 298 Kelvin to 308 Kelvin usually increases the rate. And so basically it's not linear in how that does. It's also important to note that changing the temperature does not affect the rate order, so the mechanism of the reaction. It just affects the K value. So that's why I've emphasized that the K value is specific to a certain temperature, which usually we do 25 degrees Celsius, but it is set for a certain temperature. So remember that the particles not only have to collide with sufficient energy, but they also have to have the right orientation. But the right amount of energy is what temperature affects, okay? So rate is proportional to the number of collisions per unit time, but it's not equal because not all collisions are successful. So just because you make them move faster doesn't mean you're orienting them any better. And so we have to break that minimum energy requirement, which is known as the activation energy. You have to break the bonds, okay? So a certain amount of energy has to go in. And so that is what's changing when you increase the temperature, is you're changing that activation energy that the particles have. But we're going to look at kind of the spread of what happens there. So we've looked at energy diagrams before. This is just to remind you of them. And the transition state theory says that at collision, the reactant molecules come together to form the activated complex, which is unstable. It's an unstable grouping of atoms that can then break up to form the products. So, you know, this is showing the nitrogen dioxide and carbon monoxide colliding, the right orientation with the right amount of energy, and they form this kind of activated complex. This, however much energy it takes to get there, is the activation energy, which this one is labeled. And then this is unstable, so it doesn't last. And then, so when the bonds break, they release a certain amount of energy, and then the overall change is here. And just to remind you, like, right, so reactants have more energy than the products. This would be exothermic, and it would feel hot to us because the energy released, more energy is released than goes in. So it would feel warm to the surroundings. We're part of the surroundings, so it would feel warm to us for this one. So let's look at a temperature curve, okay? So here's why, like, changing the temperature by 10 doubles the rate. So if you just look at, this is a distribution at a certain temperature, the kinetic energy that the particles have. Remember that temperature is a measure of the average kinetic energy. So this is why you have what's called a Maxwell-Boltzmann distribution for the particles. And if you have, you know, a lower activation energy, whatever the amount of activation energy is, so this is showing that, like, okay, if the particles have this much energy, then all the particles above that threshold could then react. If you have a different reaction that, you know, has a higher activation energy, then it kind of, like, you can see that less particles have the ability to, if they were to collide with the right orientation, they would then be able to react. But temperature, how the distribution shifts, okay, is you've got this orange curve, but when you increase the temperature, it usually actually flattens out the curve, makes it a little bit wider, is you actually get more particles that have the that kind of meet that minimum threshold. So the orange or the solid color here represents the temperature 1, but you can see if you increase the temperature, the areas under those curves is about 2 times when you increase it by 10 degrees. That's what this one is trying to show. So if you have more particles that meet the minimum activation energy, that's how you get the increase in rate. And just to kind of put these, just to show you, this one is showing a way more increase in temperature, but this is just called the Maxwell-Boltzmann distribution. And so just so you see, like, oh, like if you're at a lower temperature, you have a higher peak, and you can get the average kinetic energy. That's what that's showing, 100, 200, 400. You just see how, like, as temperature increases, you get a less steeper curve. But if the activation energy, let's say for a certain reaction here, was at this point, you know, the red one essentially has very few molecules that meet it. The blue one, you know, you have a larger area, and the green one, way more. So that's what this is. Plotted against an energy diagram here. Okay, so this is percentage of molecules, and this is the kinetic energy colliding molecules at certain temperatures. And you can kind of see here, so this is then lining it up with our energy diagram for an endothermic reaction. The minimum energy that the particles have to have is right here. Okay, so only these particles, the reactant molecules that have the sufficient energy, can undergo the chemical reaction. And so you can see over here that the area under the blue curve is less than the area under the red curve. So that's just showing you how temperature affects the reaction rate there, as it just gives the particles more kinetic energy. But because collision theory says that you also have to have the particles oriented, and the complexity of the molecule can kind of limit that, that is why temperature doesn't like exponentially change the rate and whatnot, because orientation isn't affected just because you make the particles move faster. So, but you have more collisions, so you just have like a higher percentage of particles that can collide there. And we already talked about the activated complex, just showing you that, and that it's unstable. The molecules, the in-between stuff is not stable, very, very high energy, and the universe is lazy and it does not want to keep it there. So it's going to react and form the new more stable products, and that's kind of what moves the reaction forward. So that's what temperature does on rate. Surface area is another one. So just see, the main three are concentration, temperature, surface area, I guess 4, and then the 4th one's catalyst, but we'll talk about catalysts in a different video lecture. So some students asked about this, you know, like, so why does it really matter with solids and whatnot? So just want to kind of break this down. So the size of the chunk, if it's a solid, then if it's a reactant or a catalyst, can impact the rate of reaction. If you have more surface area, then you have more chances for the other molecules that are hitting that solid to then react, okay? And samples that are separated at the particle level will react the fastest. So if you have particles in aqueous solution, liquids, or gases, because the particles have more random motion. But if you have a solid, then a powder would be faster than a big chunk or just like a flat piece. And it's just about maximizing collision opportunities. So you can see here, you know, if you have this magnesium atom and it is a solid chunk, the particles just only have so much area to hit that chunk, versus if they're in smaller pieces, there's just more chances. So I just wanted to show that. And then we're going to then get into these mechanisms and kind of where the rate law comes from. And that's what the next part of kinetics is going to show us.